which is based on 3D 4D printing of absorbable and deployable biliary stents. So this is a schematic of bile duct anatomy in humans. Bile duct connects the gallbladder to the pancreas and it transports bile between these organs. Bile is an important digestive fluid. Now, due to multiple clinical disorders like liver cancer, pancreatic cancer, or benign disorders like traumatic injury to the abdomen, the bile duct tends to get occluded or blocked very frequently. Now, in the event of such blockage, stents are typically used to clear the obstruction and ensure smooth flow of bile. Now, the clinically available stents are mostly restricted to plastic and metallic stents, both of which are non degradable, which means the patient has to undergo a revision surgery to remove the stent, which incurs additional healthcare costs and hospital stays and additional pain to the patient. So, we focus on absorbable stents based on PLA like polymers and we create them by using 3D printing to have patient specific constructs. Now, using conventional 3D printing, we can only have length up to 10 and diameters up to 4 which is where we utilize the concept of 4D printing, which means we have a shape change over time. So we start with a rectangular sheet printed using design anisotropy in the structure. So we have bottom and top layers stacked by transverse and longitudinal layers. This creates some sort of thermal stresses during the printing process, which eventually get relaxed by heating, so that we get the self rolling of this sheet into a tube. So this is confirmed by FES simulations, and the results are in good agreement with the experimental observations. So we can get a wide range of dimensions and lengths by just by varying the length and width of the rectangular sheet. And this shape change occurs within 1 minute and at around 70 degrees Celsius. Now, the additional highlight is that we also want to have the stents deployable. So, this is the original printed shape of a structure by the composite of PLAMC and iron oxide nanoparticles. In the original shape, it is not deployable, but once we deform and fix into this temporary shape, this can be easily deployed inside a glass tube. Now, once we have this deformed shape in position inside the at the site of deployment, we can start the alternating magnetic field, which can trigger the temporary shape to go back to the permanent shape. Now, this shape recovery happens within 12 seconds, and the extent of recovery is more than 99%. So, the iron oxide nanoparticles, which are embedded inside this composite, are inductively heating the entire structure and causing the structure to attain the permanent shape. Now, these biocompatible studies prove that the magnetic composites use a biocompatible in vitro as well as in vivo. And now we are trying to have the right designs of more advanced designs of stents by using these materials and manufacturing technologies. Thank you.